Okay. Okay, so I guess what we'll do then is we'll just listen to this. We'll listen to this talk by the guest. What's her name? Margaret Mitchell, whatever. So I'm going to go ahead and play that at 1.5 speed, and then we can get together afterwards and discuss it. So adjust the speed to 1.5 and start. Let me know if you hear it. I want to. Can you hear that?
Nope.
Wow. Can you hear that?
Nope.
Hello? You
No.
Can't hear it. Oh.
Nope.
Yeah, it's weird. When I put my headphones on, when I play it into my headphones, you can't hear it. And I know there's a way. Let me figure out how to. I could take my headphones off and play it, and then you would hear it. But let me just see if there's a way to do that. Switch to. Audio settings. So audio settings has I thought there was a way to fix this so that everybody can hear it even when I have my headphones on. Okay, well, I'm just going to take my headphones off. I'm going to put it on the speaker and then you'll hear it. Let's see. Okay. Devices. Okay. Now I'm going to start it again. And let's see if you can hear it.
Okay, hi everyone. Let's get started. So Chris is traveling this week, so he's not here, but I'm very excited to say this.
Can you hear that?
Yeah.
Okay.
Can't see it though.
Pardon?
I can't see the video.
You can't see the video. Oh, okay. Let me go ahead and reshare it. It says I'm sharing it, but I'll reshare it. Okay, are you seeing the video now?
Yeah, I can see it now, yeah.
Okay, and this is their very high energy Stanford TA. So when she talks, to give the introduction, she's talking at 1.5 speed, but it sounds like she's talking at 3 speed. But I think hopefully the lecture. So here goes.
Today we've got Margaret Mitchell, who is a senior research scientist at Google AI, and she's going to tell us about the latest work defining and understanding and improving the situation with bias in artificial intelligence. Margaret has a background working in NLP and deep learning, so I'm really interested to hear what she has to say today. Take it away.
Great, thank you. Can you guys hear me okay? I'm not sure if this mic is exactly picking up my voice. Everything's cool? Okay, cool. So this work is the product of a ton of different people and collaborators that I've tried to put up here. Some students at Stanford, also Johns Hopkins, Google, Facebook, and Microsoft are all represented. Cool. So for those of you who haven't seen this set of slides before, what do you see here? Just shout it out. Bananas. Okay, what else? Stickers. What else? Gold. Store. Shelves. What else? Bunches of bananas. What else? So you can, yeah, right, bananas. Good. So you can bananas with stickers on them. You can start doing like embedded clauses, you know, bunches of bananas with stickers on them on top of the store. Get kind of crazy.
I think I'm going to slow it down to 1.25. What do you think?
Yeah, that would be helpful.
Yeah, okay. Okay, here goes.
Something like this, we might say green bananas, or we might say unripe bananas. Given an image like this,
Hey, Joseph, that took the sound away when your other window came up.
And there is no sound either?
Yeah, I can't hear anything now.
Sorry for the interruption. I'm going to just put the screen back now. Make sure that everybody sees that now.
Yep.
Yeah, okay, here goes. Continue.
that we access as we're operating.
Gone again? The sound is gone back. Joseph, we can't hear.
So this is a riddle
okay,
that
okay.
Came back.
a little bit more
Came back, fine.
Oh, it came back?
Yeah.
Okay, here goes. Oh, you know what? It had, I see. Okay, here goes. It's coming through my microphone, so I have to leave my microphone on. So that's it. Okay, here goes.
Might have heard it before. A man and his son are in a terrible accident and are rushed to the hospital in critical care. The doctor looks at the boy and exclaims, "I can't operate on this boy. He's my son. How could this be?" Two dads, or he has a mom who's a doctor, right? Otherwise known as a female doctor, which might be contrasted with doctor. In a study they did when they first sort of put forward this riddle at Boston University, they found that the majority of test subjects overlooked the possibility that the doctor could be a she. And that included men, women, and self-described feminists. So the point is that these kinds of ways of talking about things and assumptions that we make aren't necessarily something that speaks to negative intent, but something that speaks to how we actually store representations in our minds and how we access those representations as we interact in the world. So this affects what we can learn when we're learning from text. So this is work from 2013, where they took a look at what was sort of most likely. What would you learn if you were just learning from raw text? What were some things that were common in the world? And they found that in this setup, something like murdering was 10 times more likely than blinking. And the reason for this is because people tend not to mention these typical things that go without saying. We don't tend to mention things like blinking and breathing, but we do mention atypical events like murder. And that affects the kind of things a machine can learn from text that we put out in the world, because it's been subject to all of these filtering processes that we have as humans before we communicate. This issue in particular is known as human reporting bias, which is that the frequency with which people write about actions, outcomes, or properties is not a reflection of real world frequencies or the degree to which a property is characteristic of a class of individuals, but says a lot more about how we're actually processing the world and what we think is remarkable. So this affects everything a system can learn. In a typical machine learning paradigm, one of the first steps is to collect and potentially annotate training data. From there, a model can be trained. From there, media can be filtered, ranked, aggregated, generated in some way. And from there, people see the output. And I like to think of this as a relatively straightforward pipeline, but at the very start, even before we're collecting the data, actually within the data itself are a host of different kinds of human biases. So things like stereotyping, things like prejudice, things like racism, and that's embedded within the data before we collect it. Then as we collect and annotate data, further biases become introduced. So things like sampling errors, confirmation bias, in-group bias and out-group bias. And I'll talk about these a little bit. Oh, and I should mention, feel free to ask questions as I go. Totally fine to just kind of interact throughout. So here are some of the biases that I think are relatively important for work in AI machine learning. There's hundreds you can go into, but some of the ones that I've sort of become the most aware of working in this space are this set, and I'll go through each of these a bit. So I talked about reporting bias earlier, which affects what we can learn from text. Another example of a kind of bias that really affects what we can learn from text is selection bias. So a lot of times when we get data annotated, we do something like Amazon's Mechanical Turk. And the distribution of workers across the world is not an even sort of uniform distribution. It's actually concentrated in India, the US, and then some in Europe. So this leaves out South America, this leaves out Africa, this leaves out a lot of China. And that affects the kind of things that we'll be able to learn about the world when we have things annotated. Another kind of bias is outgroup homogeneity bias, which is the tendency to see outgroup members as more alike than in-group members. And this is going to affect what people are able to describe and talk about when they're annotating things, such as emotion. So, for example, we have these two like adorable puppies on the left here, and they're looking at these 4 cats. These are all different black cats, very different in different ways, but the 2 puppies look at the cats and they see 4 cats basically the same. And it's kind of trivial to understand how that also extends to human cognition and how we also process people. It's the sense we have that the cohort that we're in, the people that we interact with, those are the kinds of people that are nuanced. And everybody else is somehow less nuanced, has less detail to them. It's a trick our minds play on us in order to help us process the world, but it affects how we talk about it, and it affects further how we annotate it. This leads to stuff like biased data representations. So it's possible that you have an appropriate amount of data for every possible human group you can think of in your data, but it might be the case that some groups are represented less positively than others. And if we have time, I'll go into a longer example of that. It also leads to things like biased labels. So this is an issue that came up when we were getting some annotations for inclusive images competition, asking people to annotate things like bride and wedding and groom. And we found that given 3 different kinds of bride, wedding, and groom images, ones that were more Western European American got the appropriate labels, and ones that weren't just got sort of more generic person kinds of labels, not able to actually tease out what's actually happening in these images. Compounding this issue are biases in interpretation when the model outputs its decisions. So one issue is confirmation bias, which is the tendency to search for, interpret, favor, recall information in a way that confirms pre-existing beliefs. And so a lot of times when we build end-to-end systems and try and test our hypotheses, we're kind of just testing it towards things that we want to be true and analyzing the results in a way that will help confirm what we want to be true. Overgeneralization, which is coming to a conclusion based on information that's too general or not specific enough. This is an issue that happens a lot of times in the analysis of deep learning model results, where it's assumed that there's some kind of general conclusion that can be taken away, when really it's actually just an effect of really skewed data. This is also closely related to overfitting, which is kind of the machine learning version of overgeneralization, which is where you're still making predictions and outcomes, but it's based on a small set of possible features. So it's not actually capturing the space of the correct features for the outcome, the desired output prediction correctly. There's also correlation fallacy, which is confusing correlation with causation. And this happens a lot, again, in talking about what machine learning models are learning and deep learning models are learning in particular, where just because things happen together doesn't mean that one is causing the other. But models don't tell you anything, deep learning models directly don't tell you anything about the causal relations. And so it's easy to think that some output that is predicted based on a correlation is actually something that's causal. And I'll talk about some examples of this too. A further issue is automation bias. And this really affects the machine learning models we put out there in the world that then get used by people in systems like justice systems. So that's the tendency to favor the suggestions of automatic predictions of models that output predictions over the different kinds of suggestions of another human. And this happens even in the face of contradictory evidence. So if a system is telling you, this is the score, or this is the risk of this individual, then we're more likely to think it's true because it came out of a mathematical system. And we automatically sort of see this as something more objective, something more mathematical, that something's going to be more true than humans somehow. And that's automation bias. So rather than this kind of clean, straightforward pipeline that we have in machine learning, we have human bias coming in at the very start in the data, and then human bias coming in data collection, annotation, and then further getting propagated through the system as we train on that data, as we start putting outputs based on that data, as people act on that data. And this creates a feedback loop where the kinds of things that we output for people to act on then serves as further training data for input for a new system. So you end up amplifying even further these different kinds of implicit biases. This is known as a bias network effect or bias laundering, I like to call it. So the message is that human data perpetuates human biases, and then as machine learning or deep learning learns from human data, the result is a bias network effect. So I want to steer clear of the idea that if I say bias or if someone says bias, that equals bad. It's a little bit more nuanced than that. So there are all kinds of things that people mean when they're talking about bias. And even the same bias can be good in some situations and bad in some situations. So bias in statistics and ML, we talk about the bias of an estimator, which is the difference between the predictions and the truth, the ground truth. We talk about the bias term in linear regression. We also have cognitive biases, and I talked about that in the beginning, and not all of those are negative or have to be seen as negative. So optimism is another kind of bias that we can have that affects our worldview and the way we sort of process things. And even things like recency bias and confirmation bias are just ways that our minds can handle the combinatorial explosion of all the different things that can be true in the world and put it down to something tractable that we can sort of operate with in the real world. So algorithmic bias is what a lot of people mean in headlines and whatnot when they're talking about bias, which is more about unjust, unfair, or prejudicial treatment of people. That's an output of the automated decision system. And the focus here is really on unjust, unfair, or prejudicial treatment of people. So a lot of the work in this space right now is focusing on trying to understand what does it mean to be unjust from an algorithm? What does it mean to be unfair from an algorithm? And how can we handle this? How can we sort of mitigate these issues in order to be able to keep developing technology that's useful for people without worsening social divides? And I thought The Guardian put it really well a few years ago. They said, although neural networks might be said to write their own programs, they do so towards goals set by humans, using data collected for human purposes. If the data is skewed, even by accident, the computers will amplify injustice. And I really keyed in on this amplify injustice idea. And let's talk about what that can mean. So one of the avenues of deep learning research that's taken off in the past few years is predicting criminal behavior. How many of you are familiar with predictive policing? Okay, like half of the class. Okay, so in predictive policing, algorithms predict areas to deploy officers where crime is considered to be likely to occur. But the data that the models are trained off of is based on where police officers have already gone and made arrests. So the systems are simply learning the patterns of bias that humans have and where they go and where they are trying to decide to find crime, and then reflecting them back. So because the system hones in on some of the top spots where people have been arrested, notice that's not the same thing as where crimes have been committed, right? It's where arrests have been made. It means that the other areas that might be explored for crime don't get explored at all. That worsens the situation. Some neighborhoods get really acutely focused attention on them, and that heightens the chances of serious repercussions for even minor infractions. That means arrests, and that means a feedback loop of data that you will get an arrest in this place if you go there. Another sort of related issue in this space is predictive sentencing. So there was a really nice article that came out from ProPublica a few years ago discussing this. But when most defendants are booked in jail, they respond to a questionnaire called Compass. And their answers are fed into this software system that generates scores that correspond to the risk of recidivism. That's the risk of making a crime again. And the questions are used to gather data on the defendant's socioeconomic status, family background, neighborhood crime, employment status, and other factors in order to reach some prediction of an individual's crime or criminal risk. But what ends up happening is that it ends up focusing on the key bias issues that humans have and propagating it back with something that looks like an objective score. So you're a lot more likely to be convicted of a crime if you're Black than if you're white, even if you've made the exact same crime. And the system will pick up on this and will reflect this back to say that people who are Black are more likely to have recidivism, more likely to to make a crime again. So this is an example of automation bias, preferring the output of a system in the face of overgeneralization, feedback loops, and correlation fallacy, confusing things that are occurring together as being somehow causal. There's another sort of area of research and startups looking at predicting criminality in particular from things like face images. So there's a company out there called Faceception. They're based in Israel, and they claim to be able to use individual images with computer vision and machine learning technology for profiling people and revealing their personality based only on their facial image, recognizing things like high IQ, white-collar offender, pedophile, and terrorist. And their main clients are Homeland Security, lots of other countries dealing with sort of public safety issues. They've not published any details about their methods, their sources of training data, or their quantitative results. We know that in light of automation bias, people will tend to think it just works, even when it doesn't work well. But there was a paper that came out in a similar line predicting criminality or purporting to predict criminality from individual face images. And that one had some results and some more details about the data that we could kind of dig into to understand where are these kinds of claims coming from. So this was an article that was posted on Archive near the end of 2016. And they said they were using less than 2,000 closely cropped images of faces, including wanted suspect ID pictures from specific regions. And they claimed that even based on this very small training data set, that they were able to predict whether or not someone was likely to be a criminal, greater than 90% accuracy. And they got so lost in this idea that it's sort of funny to read to just take a step back and realize what's actually happening. So for example, one of their really great exciting claims was that the angle theta from nose tip to two mouth corners is on average 19.6% smaller for criminals than for non-criminals. This is otherwise known as smiling, and might be, exactly the kind of images people would use when trying to put out wanted criminal pictures, probably not really happy pictures. But you get so lost in the confirmation bias, you get so lost in the correlation and the feedback loops that you end up overlooking these really obvious kinds of things. So that's an example of selection bias, experimenter's bias, confirmation bias, correlation fallacy, and feedback loops all coming together to create a deep learning system that people think is scary and can do things that it can't actually do. One of the issues with this was that the media loved it. Like, it was all over the news, and there's been similar kinds of things happening again and again. The media wants to sell the story. And so it's part of our job as researchers, and people who work on this stuff, to be very clear about what the technology is actually doing and make a distinction between what you might think it's doing and what it's actually doing. So another issue that has come up recently is claiming to be able to predict internal qualities, but specifically ones that are subject to discrimination and loss of opportunity. So in particular, there was this work that came out that claimed to be able to predict whether or not someone was homosexual just based on single face images. Now it's important to know that the images that they used in the study included images that were from dating websites where people self-identified as straight or gay and identified as whether they were looking for a partner who was straight or gay. And these became the sources of the training data. And still from this, oh, before I go on, can you guys just understand just from that what the issue might have been.
Rainbows.
I don't know that there was actually anything about rainbows, but that's really unfortunate. Yeah. Someone in the back, yeah.
Presenting themselves differently.
Right, yeah. So this has more to do with the presentation of the self, the presentation of the social self when you're trying to, for example, attract a partner on a website, and less to do with how you look day to day. And yet they kind of went to these large conclusions that aren't supported at all by the data or by their study, but things like consistent with the prenatal hormone theory of sexual orientation, gay men and women tended to have gender atypical facial morphology. Now, none of the authors actually were prenatal hormone theory specialists. You know, they had doctor in their name, so maybe that's a thing. This was a Stanford professor, and like I've presented this a few times at Stanford and gotten into some like pretty harsh fights about this. So I'm ready if anyone wants to take me on. But me and my some of my colleagues decided we'd play around with this a bit. And what we found was that a simple decision tree. So I'm kind of assuming you guys know what a decision tree is. Okay, cool. So based on wearing makeup or wearing glasses, got us pretty close to the accuracy reported in the paper. That says nothing about internal hormones, that says nothing about any of that, and says a lot about the physical presentation, the things that are on the surface. It says a lot more about how people are presenting themselves than what is happening internally. So the key thing that's recently kind of been overlooked is that deep learning is somehow, it's sort of considered that it's somehow magically going beyond surface level. But the point is that it's working on the surface level and working well. And in the face of confirmation bias and other kinds of bias factors, it's easy to assume that something else is happening that's not. Without critical examination, for example, simple baselines, simple sanity checks, these kinds of things can just be ignored and not noticed at all. So that's an example of selection bias, experimenter's bias, and correlation fallacy. Okay, so now I'm going to talk about measuring algorithmic bias. So I just said a lot about different kinds of biases that come in the data, in the collection, in the interpretation of the results. Let's talk about actually quantitatively measuring different kinds of biases. So one of the key things that's emerged in a few different works and really ties nicely to a lot of fairness work is this idea of disaggregated evaluation. So in disaggregated evaluation, you evaluate across different subgroups as opposed to looking at one single score for your overall testing data set. Okay, you guys are probably familiar with the training testing data split. You kind of train on your given training data, you test on your given testing data, and you report like precision, recall, F-score, things like that. But what that masks is how well the system is actually working across different kinds of individuals and across different subgroups. And so one just straightforward way to handle this is to actually evaluate with respect to those different subgroups. So creating for each sort of subgroup prediction pair. So for an example, you might look at women face detection, men face detection, and look at how the error rates are different or similar. Another important part of this is to look at things intersectionally, combining things like gender and race at the same time, and seeing how the error rates on those sorts of things change and how they're different across different intersections. And this is inspired by Kimberly Crenshaw, because she pioneered intersectional research in critical race theory. And she discussed the story of Emma DeGraff and Feed, who was a woman at General Motors. And she claimed that the company's hiring practices discriminated against Black women. But in their court opinion, the judges ruled that General Motors hired many women for secretarial positions and many Black people for factory roles, and thus they could not have discriminated against Black women. What they failed to do was look at the intersection of the two and understand that the experience there might be fundamentally different than any of the experiences of either of these sort of subgroups in isolation. And the same becomes true when you start looking at errors that are regularly made in deep learning systems. So we've been able to uncover a lot of different kinds of unintended errors by looking not only at the disaggregated evaluation, but also at intersectional disaggregated evaluation. So I'm going to walk through a bit how this works. This is probably going to be review for most of you, but I think it's really important to understand this because it also ties to how we measure fairness. And when we say like algorithmic fairness, what we're talking about. So the confusion matrix is a way, you guys, okay, are you guys familiar with the confusion matrix? Sorry, just want to know where, okay, awesome, cool. So familiar with the confusion matrix, right? So you have model predictions and references, and you can kind of look at these as negative and positive, binary classification kind of approach here, where if the ground truth says something is true and the model predicts it's true, it's a true positive. If the ground truth says it's false, and the model predicts it's false, it's true negative. And the errors, the kind of different issues that arise are false negatives and false positives. So in false positives, the ground truth says something is negative, but the model predicts that it's positive. And then in false negatives, vice versa. From these, basic kind of, this basic breakdown of errors, you can get a few different metrics. These metrics actually trivially map to a lot of different fairness criteria. So for example, if we're looking at something like female versus male patient results and figuring out things like precision and recall, which is relatively common in NLP, if you have equal recall across your subgroups, that's the same as the fairness criteria of equality of opportunity. I could work through the math, but I mean, this is basically just the main point that it says that given that something is true in the ground truth, the model should predict that it's true at equal rates across different subgroups. So this ends up being equivalent to having the same recall across different subgroups. Similarly, having the same precision across different subgroups is equivalent to a fairness criterion called predictive parity. And so as fairness has been defined again and again, it was originally, some of these definitions came in 1966 following the Civil Rights Act of 1964. They were reinvented a few times and most recently reinvented in 2016. But they all sort of boil down to this disaggregated comparison across subgroups, and the math, the metrics end up being roughly equivalent to what we get from the confusion matrix, specifically in classification systems. So which kind of fairness metric do you use? What are the different criteria you want to use to look at the differences across different subgroups? That really comes down to the trade-offs between false positives and false negatives. So this is the same problem that you're dealing with when you're just figuring out how to evaluate generally. There's no one fairness criterion that is the fairness criterion to rule them all. Deciding which one is better than the other is the same as kind of trying to decide which is better, precision or recall, right? It depends on what the problem is and what you're interested in measuring. So a case where false positives might be better than false negatives, and so you want to prioritize something like a false positive rate across subgroups is privacy and images. So here a false positive is something that doesn't need to be blurred gets blurred. That's just kind of a bummer. But a false negative would be something that needs to be blurred as not blurred, and that can be identity theft. It's a much more serious issue. And so it's important to prioritize the evaluation metrics that stress the false negative rates. An example where false negatives might be better than false positives is in spam filtering. So a false negative could be an email that's spam not caught, so you see it in your inbox. It's usually just annoying, it's not a big deal. But a false positive here would be email flagged as spam and then removed from your inbox, which, if it's from a friend or a loved one, it can be a loss, maybe a job offer, something like that. Right, so I just kind of covered how AI can unintentionally lead to unjust outcomes, and some of the things to do, or some of the things to be aware of here, are the lack of insight into sources of bias in the data in the model, lack of insight into the feedback loops from the original data that's collected as an example of what humans do to the data that's then repurposed, reused, acted on, and then further fed in. A lack of careful disaggregated evaluation, looking at the disparities, the differences between different subgroups in order to understand this bias, this difference across the subgroups. And then human biases in interpreting and accepting and talking about the results, which then kind of further the media cycles and the hype around AI right now. But it's up to us to influence how AI evolves. So I like to think of this in terms of short-term, middle-term, and long-term objectives. So short-term today, we might be working on some specific model where we're trying to find some local optimum. We have a task, we have data, something like that. And that's sort of short-term objectives. We might have a slightly longer-term objective of getting a paper published, or if you're in industry, like getting a product launched, whatever it might be. From there, we might see our next endpoint as getting an award, or maybe you become sort of famous for something for a few minutes, something like that, and that's cool. But there's a longer-term objective that we can work towards as well at the same time. And that's something like a positive outcome for humans and their environment. So instead of just kind of focusing on these local decisions, these local optimum, and these sort of local paper-by-paper based approaches to solving problems, you can also kind of think about what's the long-term objective. Where does this get me as I trace out an evolutionary path for artificial intelligence down the line in 10 years, 15 years, 20 years? And one of the ways you can address this is by thinking, how can the work I'm interested in now be best focused to help others? And that involves talking to experts and kind of going outside your bubble, speaking across interdisciplinary fields like cognitive science, which I've just talked a bit about. So let's talk about some things we can do. So first off is data. So a lot of the issues of bias and fairness in machine learning models really come down to the data. Unfortunately, in machine learning and deep learning, working on data is really not seen as sexy. There's a few data sets that people use. They're out there. That's what people use. And there's not a lot of analysis done on how well these data sets capture different truths about the world, how problematic they might be. But it's a pretty wide area that needs a lot of future additional work. So work on understanding the data skews and the correlations. If you understand your data skews and the correlations that might be problematic in your data, then you can start working on either models that address those or data augmentation approaches in order to sort of make the data set a little bit better or a little bit more representative of how you want the world to be. It's also important to abandon the single training set, testing set from similar distribution approach to advancing deep learning. So when we do projects in deep learning, we tend to have the training set and the testing set, and then that's what we sort of benchmark on and prioritize. But the point is, as you move around different testing sets, you're going to get vastly different results. And so by keeping in this just sort of one training testing data set paradigm, you're really likely to not notice issues that might otherwise be there. And one way to really focus in on them is having a hard set of test cases that you really want to make sure the model does well on. So these are things that are particularly problematic, things that would be really harmful to individuals if they were to experience the output. And you kind of collect those in a small test set, and then it's really easy to evaluate on that test set as you benchmark improvements on your model, as you add different kinds of things to your model, in order to see not just how your model is doing overall in terms of your testing data set, but how well you're doing in terms of these examples you really want it to do well on, that you know that is going to be a problem if it doesn't do well on. And any sort of degradation in that, you might want to prioritize to fix above degradation and overall accuracy. And it's also important to talk to experts about the additional signals that you can incorporate. So we put out a tool to help with this, understanding data skews called Facets. It's just available there. And it's a really handy kind of visualizer for slicing, understanding what some of the differences are between different subgroups and different representations, and you can sort of dig in and explore a bit more. So this is just to sort of help people come to terms with the data that they're actually using and where there might be unwanted associations or missing kind of features. Another approach that's been put forward recently, specifically on the data side, is this data sheets for data sets approach. So this is this idea that when you release a data set, it's not enough to just release the data set with like some pretty graphs and like talking about basic distributional information. You need to talk about who the annotators were, where they were, what the inter-annotator agreement was, what their background information was, motivation for the data set, all these other kinds of details. So now you actually know that this isn't just a data set. This is a data set that has these specific biases. There's no such thing as a data set that isn't biased in some way. A data set, by virtue of the fact that it's collected from the world as a subset, is a biased set of the world in some way. The point is to make it clear what it is, how it is biased, what are the various biases that are important to know about in the data set. So that's one of these ideas behind data sheets for data sets, releasing these data sets publicly. All right, now let's switch a little bit to machine learning. So there are a couple techniques that I like to use. I'll talk about two. One is bias mitigation, which is removing the signal for a problematic output. So removing stereotyping, sexism, racism, trying to remove these kind of effects from the model. This is also sometimes called debiasing or unbiasing, but that's a little bit of a misnomer because you're generally just kind of moving around bias based on a specific set of words, for example. So to say it's unbiased is not true, but you are kind of mitigating bias with respect to some certain kinds of information that you provide it with. And there's inclusion, which is then adding signal for desired variables. So that's kind of the opposite side of bias mitigation. So increasing model performance with attention to subgroups or data slices with the worst performance. In order to address inclusion, kind of adding signal for underrepresented subgroups, one technique that's worked relatively well is multitask learning. So I've heard that you guys have studied multitask learning, which is great. So I'll tell you a bit about a case study here. So this is work I did in collaboration with a UPenn World Wellbeing Project, working directly with clinicians. And the goal was to create a system that could alert clinicians if there was a suicide attempt that was imminent. And they wanted to understand the feasibility of these kinds of diagnoses when there were very few training instances available. So that's similar to kind of the minority problem in data sets. In this work, we had two kinds of data. One was the internal data, which was the electronic health records that was either provided by the patient or from the family. It included mental health diagnoses, suicide attempts or completions, if that were the case, along with the user's, the person's social media data. That was the internal data that we did not publish on, but that we were able to work with clinicians on in order to understand if our methods were actually working. The external data, the proxy data, the stuff that we could kind of publish on and talk about was based on Twitter. And this was using regular expressions in order to extract phrases and Twitter feeds that had something that was kind of like diagnoses. So something like, I've been diagnosed with X, or I've tried to commit suicide. And that became kind of the proxy data set and the corresponding social media feeds for those individuals for the actual diagnoses. And the state of the art in clinical medicine, kind of until this work, there's been more recently, but is sort of this single task logistic regression setup where you have some input features and then you're making some output predictions like true or false. You can add some layers and start making it deep learning, which is much fancier. You can have a bunch of tasks in order to do a bunch of logistic regression tasks for a clinical environment. Or you can use multitask learning, which is taking a basic deep learning model and adding a bunch of heads to it, predicted jointly at the same time. And here we had a bunch of diagnosis data. So we predicted things like depression, anxiety, post-traumatic stress disorder. We also added in gender because this is something that the clinicians told us actually had some correlation with some of these conditions and that they actually used it in making decisions themselves for whether or not someone was likely to attempt suicide or not. And this also used this idea of comorbidity. So multitask learning is actually kind of perfect for comorbidity in clinical domains. So comorbidity is when you have one condition, you're a lot more likely to have another. So people who have post-traumatic stress disorder are much more likely to have depression and anxiety. And depression and anxiety tend to be comorbid. So people who have one often have the other. So this points to the idea that perhaps there's some underlying representation that is similar across them that can be leveraged in a deep learning model with individual heads further specifying each of the different kinds of conditions. And so what we found was that as we moved from logistic regression to the single task deep learning to the multitask deep learning, we were able to get significantly better results. And this was true both in the suicide risk case where we had a lot of data, as well as the post-traumatic stress disorder case where we had very little data. The behavior here was a little bit different. So going from logistic regression to single task deep learning when we had a lot of data, as we did with the suicide risk, had the single task deep learning model working better than the logistic regression model. But when we had very few instances, this is where the deep learning models really struggled a lot more. And so the logistic regression models were actually much better. But once we started adding heads for the comorbid different kinds of conditions, the different kinds of tasks that related to whether or not the person might be committing suicide, we were able to bump the accuracy way back up again. And it's roughly 120 at-risk individuals that we were able to collect in the suicide case that we wouldn't have otherwise been able to notice as being at risk. One of the approaches we took in this was to contextualize and consider the ethical dimensions of releasing this kind of technology. So it's really common in NLP papers to give examples, but this was an area where we decided that giving examples of like depressed language could be used to discriminate against people, like at job interviews or something like that, the sort of armchair psychology approach. So we decided that while it was important to talk about the technique and the utility of multitask learning in a clinical domain and for bringing in inclusion of underrepresented subgroups, it had to be balanced with the fact that there was a lot of risk in talking about depression and anxiety and how those kinds of things could be predicted. So we tried to take a more balanced approach here. And since then, I've been putting ethical considerations in all of my papers. It's becoming more and more common, actually. So another kind of approach that's now turning this on its head, where you're trying to remove some effect, mitigate bias in some way, is adversarial multitask learning. So I just talked about multitask learning. Now let's talk about the adversarial case. And the idea in the adversarial case is that you have a few heads. One is predicting the main task, and the other one is predicting the thing that you don't want to be affecting your model's predictions. So for example, something like whether or not someone should be promoted based on their performance reviews and things like that. You don't want that to be affected by their gender. Ideally, gender is independent of a promotion decision. And so you can create a model for this that actually puts that independence criteria in place by saying, I want to minimize my loss on the promotion while maximizing my loss on the gender. And so how we're doing that is just predicting gender and then negating the gradient. So removing the effect of that signal. This is another adversarial approach. So you might have been familiar with like generative adversarial networks. So this is like two discriminators, two different task heads, where one is trying to do the task that we care about, and the other one is removing the signal that we really don't want to be coming into play in our downstream predictions. So this is a way of kind of putting this into practice. So the probability of your output, predicted output, given the ground truth and your sensitive attribute like gender is equal across all the different sensitive attributes, or equal across all the different genders. And that's an example of equality of opportunity and supervised learning being put into practice. So this is one of the key fairness definitions. It's equivalent to equal recall across different subgroups, as I mentioned earlier. And that's a model that will actually implement that or help you achieve that, where you're saying that a classifier's output decision should be the same across sensitive characteristics, given what the correct decision should be. Okay, so how are we on time? Are there any questions so far? We good? Okay, cool. So I'm going to go into a little bit of a case study now, an end-to-end system that Google has been working on, my colleagues have been working on, that is in the NLP domain and deals with some of these bias issues. So you can find out more about this work in papers at AIES in 2018 and FAT STAR Tutorial 2019 called Measuring and Mitigating Unintended Bias in Text Classification. And this came out of Conversation AI, which is a product that's it's part of this, it's called a bet at Google. It's a kind of spin-off company called Jigsaw that focuses on trying to combat abuse online. And the Conversation AI team is trying to use deep learning to improve online conversations and collaborate with a ton of different people to do that. So how this works is, you can try it out too on perspectiveapi.com. So given some phrase like "you're a dork," it puts out a toxicity score associated to that, like 0.91. And the model starts sort of falsely associating frequently attacked identities with toxicity. So this is a kind of false positive bias. So I'm a proud tall person gets a model toxicity score of 0.18. I'm a proud gay person gets a toxicity model score of 0.69. And this is because the term gay tends to be used in really toxic situations. And so the model starts to learn that gay itself is toxic, but that's not actually what we want. And we don't want these kinds of predictions coming out of the model. The bias is largely caused here by the data set imbalance. Again, this is data kind of coming and rearing its head again. So frequently attacked identities are really overrepresented in toxic comments. There's a lot of toxicity towards LGBTQ identities. It's really horrible to work on this stuff. It's really, can really affect you personally. One of the approaches that the team took was just to add non-toxic data from Wikipedia. So helping the model to understand that these kinds of terms can be used in, more positive sorts of contexts. One of the challenges with measuring how well the system was doing is that there's not a really nice way to have controlled toxicity evaluation. So in real world conversation, it can be kind of anyone's guess what the toxicity is of a specific sentence. If you really want to control for different kind of subgroups or intersectional subgroups, then it can be even harder to get real good data to evaluate properly. So what the team ended up doing was developing a synthetic data approach. So this is kind of like a bias Mad Libs, where you take template sentences and you use those for evaluation. This is a kind of evaluation you'd want to use in addition to your target downstream kind of data set, but this helps you get at the biases specifically. So some template phrase like "I'm a proud blank person," and then filling in different subgroup identities. And you don't want to release the model unless you see that the scores across these different kinds of template sentences with synthetic these synthetic template sentences are relatively kind of the same across all of the different model runs. Cool. So some assumptions that they made in this was that the data set didn't have annotated bias, and they didn't do any causal analysis because they were just trying to focus in particular on this toxicity problem. They used a CNN convolutional, you guys know, with pre-trained glove embeddings. This is probably like your bread and butter, pre-trained glove embeddings. I'm sure you know all about this in Word2Vec. Cool. Keras implementation of this. And using these kind of data augmentation approaches, both the Wikipedia kind of approach, as well as actually collecting positive statements about LGBTQ identity. So there's this project called Project Respect at Google, where we go out and talk to people who identify as queer or people who have friends who do, and talk about this in a positive way. And we add this as data, so we can actually know that this can be a positive thing. And in order to measure the model performance here, again, it's looking at the differences across different subgroups and trying to compare also the subgroup performance to some sort of general distribution. So here they use AUC. where AUC is essentially the probability that a model will give a randomly selected positive example a higher score than a randomly selected negative example. So here you can see some toxic comments and non-toxic comments with example sort of low AUC. Here, this is an example with a high AUC, so the model is doing a relatively good job at separating these two kinds of comments. And there are different kinds of biases that they've defined in this work. So low subgroup performance means that the model performs worse on subgroup comments than it does on comments overall. And the metric they've introduced to measure this is called subgroup AUC. Another one is subgroup shift. And that's when the model systematically scores comments from some subgroup higher. So this is sort of like to the right. And then there's also this background positive subgroup negatives shifting to the left. Yeah, that's sort of saying what I said. It can go either way, to the right or the left, and there's just kind of different metrics that can define each of these. Cool. And the results in this sort of going through, not only just looking at, qualitative examples and general evaluation metrics, but also focusing in on some of the key metrics defined for this work, these sort of AUC-based approaches. They were able to see significant differences in the original release, which didn't account for any of these unintended biases, and downstream releases, which incorporated this kind of normative data that said the sort of things that we thought the model should be learning. Cool. So the last thing to keep in mind as you sort of develop and work towards creating deeper, better models is to release responsibly. So this is a project I've been working on with a ton of different people called model cards for model reporting. It's a little bit of like the next step after data sheets for data sets, where data sheets for data sets focus on information about the data. Model cards for model reporting focuses on information about the model. So it captures what it does, how it works, why it matters. And one of the key ideas here is disaggregated and intersectional evaluation. So it's not enough anymore to put out human-centered technology that just has some vague overall score associated to it. You actually need to understand how it works across different subpopulations, and you have to understand what the data is telling you that. So here's some example details that a model card would have, who it's developed by, what the intended use is, so that it doesn't start being used in ways that it's not intended to be used. The factors that are likely to be affected by disproportionate performance of the model, so different kinds of identity groups, things like that. The metrics that you're deciding to use in order to understand the fairness of the model, or the different performance of the model across different kinds of subgroups and factors. Information about the evaluation data and training data, as well as ethical considerations. So what were some of the things you took into account, or what are some of the risks and benefits that are relevant to this model, and additional caveats and recommendations. So for example, in the conversation AI case, they're working with synthetic data. So this is a sort of limitation of the evaluation that's important to understand, because it can tell you a lot about the biases, but doesn't tell you a lot about how it works generally. And then the key component in the quantitative section of the model card is to have this both intersectional and disaggregated evaluation. And from here, you trivially get to different kinds of fairness definitions. The closer you get to parity across subgroups, the closer you're getting to something that is mathematically fair. Okay, so hopefully by paying attention to these kinds of approaches, taking into account all these kinds of things, we can move from majority representation of data in our models to something more like diverse representation for more ethical AI. Okay, that's it. Thanks.
Okay.
Let's get started. So welcome to the very final lecture of the class.
Okay. Okay, I guess that's it for that one. It's a shorter one, shorter lecture. Are there any comments? Are there any comments that people may have noticed things that they wanted to discuss? I hadn't come across that kind of adversarial, I forget what you called it, adversarial training, where you train a model with two objectives. One is to make accurate predictions, but the other one is to make sure that some unwanted characteristic doesn't affect those decisions, like gender or whatever. I thought that was interesting.
Yeah, I have a comment about that example where they had toxic comment classification. And there was that comparison of like, I'm a proud tall person versus I'm a proud gay person, and one was classified as toxic and another as not toxic. And they decided to explicitly make sure that like by plugging in those different words that those are classified the same. But for what how I see it, it's kind of masking another problem, that model doesn't actually understand what is this sentence about. It's more like triggered by one highly related to toxicity word. So
yeah.
Like a similar example I remember like mentioned somewhere, I don't know, in FastAI forums probably. And that, for those who are familiar with FastAI, their language model is demonstrated on IMDb negative or positive review data set. And there was some very straightforward for a human review, like just a person who tried to plug in something like that movie wasn't great, and model just didn't understand negation and simply predicted positive because there was a word great. And I think it's that example is a kind of demonstration of limitation of language model understanding rather than demonstration of this bias. Also, it might be a demonstration of a bias, but I think that like a more deeper problem is there.
Yeah, I think what she pointed out is that the word gay is often used as a slur when they on these, on the internet, when people say that's really gay, or they use it as a disparaging comment. But when you add in neutral text from the Wikipedia, that should help smooth things out. And what I think is that their models are so old that they didn't use the attention mechanism and the techniques that we've been learning in this class to take into account context. And I think if they had, they wouldn't have had a problem with that particular kind of construction. I bet that a model that used attention wouldn't have scored that neutral sentence, I'm a proud gay person, as a toxic comment.
There's another comment I could make. So there's a difference between saying I'm a proud gay person and he's a proud gay person. I don't think the computer picked up on that difference.
Yeah, Yeah, did they put that sentence? I don't remember. Did they put that sentence in? He is a proud gay person.
No, I think they only had the sentence, I'm a proud gay person, not
Yeah.
he's a proud gay person.
Yeah. Yeah, but it just seems to me that a model that, that a bag of words model, a really simplistic model would get that wrong. But a model that takes into account context, especially with using attention and so on, wouldn't have gotten that wrong.
I agree, Joseph, but I would be, to Arto's comment, I would be a little more circumspect about that it wouldn't have, it might not have, but the point being that these language models that we create aren't really great. We still don't clearly understand what they learn and what they represent in all its nuances. So, and there's still a lot of research going on about that getting presented, and that's kind of one of the future directions of NLP is what are the models learning and what would we wish for them to learn.
Yeah, maybe I shouldn't have said it wouldn't have, but I think it would be more likely to not have flagged that as a toxic comment. I mean, especially since we've seen Chris Manning has shown us that you can, using attention, you don't get confused by double negatives and so on. You don't get confused by those things. Yeah,
some of the simpler ones, but there's still things that language models fail to pick up that probably 5-year-olds will pick up.
Mm-hmm.
Yeah, actually, that's interesting to try out like different settings. There is like another concern which might be related to that is with increasing number of parameters, this transformer-based language models perform much better. And this, some say that this most probably is related to memorization of the text they use in some way. So, like, if a model relies a lot in memorization of a text, then it would be like more likely to be biased because it doesn't actually understand what the text is about. It just compares with the data it was trained on. But if we are closer to like really understanding the meaning, then biased data wouldn't be such a problem because like a couple of representative positive examples would be enough to, like for a human, understanding whether the word itself is negative or the word in some context is negative would be easy, but might be not so easy for a language model. Yeah, that's interesting.
Also, I wasn't convinced by that predictive policing model that she said was so awful. I mean, it's like if you're going to send, patrol cars out, you send them to areas where there's crimes being committed. I mean, and if there's new, so she's saying that some areas are getting too many police cars, and then other areas where crimes might be committed aren't getting any police cars. But as if there's a region where no crimes are committed, then all of a sudden some crimes get committed there, then you change your algorithm to set your algorithm automatically will send more police cars there next time. So I really don't understand the problem that she's pointing to with this.
On that one, actually, there are books written about it in papers to Joseph, and while I don't recall all the details, there is a fundamental premise that you just stated, which unfortunately doesn't hold, that at least in the US, cars are sent to the places where most crimes are committed. And if you largely analyze the data, that doesn't necessarily hold in many places.
But that's
It's
the algorithm, right? That's the algorithm.
where,
The algorithm is supposed to be sending cars to areas where crimes are committed, right?
but it's relying on where cars were sent previously, which is not to places where necessarily crimes were committed, but to places where arrests are made, and the two are not the same. That's the point.
Then that's a stupid algorithm. The algorithm should take into account, should be updated all the time by where crimes are committed, and that should determine where.
Right, but that's the point, right? Because there are two variables which people one is being used as the proxy for the other, where arrests are made and where crimes are committed.
Mm-hmm.
And as she said, if you listen to that, it's relying on where arrests are made.
Mm-hmm.
And at least in the US, in some localities, again, I'm being very specific, it's not always true and it's not always the case, but in the US, in some localities, it's not the case where most police cars are sent and where most crimes are committed. The two do not serve as proxies for each other.
Right. So there's an easy fix, and I don't see what the big hullabaloo is about. You just say, okay, the algorithm isn't doing its job. It should be based on where crimes are committed, and then fix the algorithm and be done with it. I mean, I don't see what's the big deal. I mean,
but it was deployed in places and had results, right? And the even more insidious thing, which is to me a bigger deal, because I think ever since I started looking into ML and AI, that I keep this is something which is incredible. Humans tend to believe that systems which don't involve people are inherently unbiased. That's something that she called out, which
automation bias.
Exactly, is shockingly true. And you would be shocked at how much people believe that.
But in this case, like as Joseph says, it's not really bias, is it? It's just a bad algorithm. Like if you want to stop crime and get the people who are committing the crime, you should be sending your police cars to where the crimes are happening, not where their arrests are made. So like that, there's just a bad algorithm as opposed to somebody being biased.
Yes, except what I don't know, and there's again research on it, is if you just did the send the cars, is that going to be any better than anything else that's currently being done? So as with most of these things, if you start looking at the details, then more details emerge. So yes, on the surface, I would agree with you and Joseph that it seems, I'll just use this other data, but I just am skeptical that it's as simple as that.
Yeah, I would say it might be that this is a kind of simple case, and it was quite easy to find the problem. But in some other cases where the same problem arises of negative feedback loop, when you like send the cars to a place, make more arrests there, and then this data is feedback to your algorithm. Here it's like kind of obvious, but in some more complicated cases, for example, this YouTube recommendation algorithms, and they are also known to cause this negative feedback loops when people got stuck in some information bubble and can't really see much information from outside of this bubble, and it might be more difficult to avoid these feedback loops. And but the algorithms are deployed and they are working and they are affecting the society.
Yeah, I've heard about that YouTube algorithm. I don't know much about it, but apparently, like it's driven by exactly how much profit you can get for YouTube, which means how many clicks people make on things. So they just tend to these systems tend to promote videos that that get obsessive, that get people to. I guess the things that get people to click on them most are videos with mean and sadistic and nasty things, negative things happening in them, and that's what attracts people the most. And so that ends up being what drives, what drives their recommendations to show people lots of content like that.
Yeah, at the risk of making people groan, those things are optimized for attention.
Mm-hmm.
Yeah. Also, like watching some, say, educational video, you can watch one video and then you need some time to process the information. But if you watch some recreational videos, you can spend much more time. And such kind of algorithm may result in like you get recommended like more and more of these recreational videos, which are much easier to watch, but actually you may have lack of more useful stuff which you might want to be recommended, but you can't spend so much time watching it,
Yeah, so like quick videos or fast, videos that take time, like educational videos, maybe they don't get a lot of click traffic or whatever. Somebody listens to them and then they're not going to go off and listen to ads and click on any ads. But short, recreational videos, like you said, people can watch it in 5 minutes and then they can go on to the next one and then they can see a new ad and then they can maybe click on it and maybe that makes more money for YouTube.
I don't know, this is a little tangential thought, but I was wondering if there is a good way of kind of managing this on YouTube, because my YouTube basically has two feeds. It's ML and comedy. And it would be interesting if I can like separate them.
Or combine the two.
Yeah, are there any
Get ML comedy?
that overlap? Yeah, are there any that overlap in those two?
Yeah, there are a couple of people who actually do poetry with ML.
Yeah, I think YouTube has tried. I think they have tried. I mean, I listened to I think Lex Friedman interviewing some guy from somebody who was in charge of the YouTube algorithm and so on, and I think they've realized that there's a problem and they've tried to tweak it, make tweaks to it. And I don't think they talk too much about the tweaks that they made, but they have tried to move it away from the kind of algorithm that would preferentially steer people towards really bad material.
Yeah, but it also would suffer from kind of the red queen effect type of thing, right? Meaning that they tweak it and the people who want to make those videos more popular will tweak to satisfy their new tweaks.
Mm-hmm. Mm-hmm.
Just like SEO or search engine optimization. Right? You make a tweak and people figure out what the tweak optimizes for and they'll tweak it for that. So it's like a rat race to see who wins.
So what did you mean by red queen effect?
It's like, this in evolution and stuff, they have this concept of how certain, the prey and what's the term for the animal that gets preyed on. So each of them evolve in order to kind of stave off that threat. So it becomes a kind of a race as to, and sometimes they reach equilibrium and sometimes they don't. Mm-hmm. And if they don't, then it could be dangerous for the environment, for the ecosystem itself, because one will tend to wipe out the other and there's no more balance left. But invariably, left alone, things seem to reach some kind of balance between the animal that hunts and the animal that gets preyed on.
Predator prey. Yeah, I just hadn't heard that term, the Red Queen effect, before. That's all I was asking what that is.
I think bias is a difficult thing to handle, because I was thinking in the problem of the police. So I guess they use it as supervised algorithm. So you can juggle with the data before and thinking that that data comes from the police and that the police itself tries to handle different the people. So I was thinking, well, just don't use a supervised algorithm, maybe a reinforcement, and at the end, if that reinforcement algorithm started to send the police to different places, I was thinking, well, these algorithms like try to explore the environment and then like try to make some good decisions. But I was thinking in the operator of the well, the policy itself. The policy itself, it has its own bias. So even on a reinforcement learning algorithm, it will start learning that bias that the police make more or find more suspicious people in black neighborhoods that on white ones. So to make an algorithm, you will not only need to train it, but you will need to teach what is racism or something like that, because if not, it doesn't matter if it will be a reinforcement learning algorithm or a or a supervised one, because at the end it will learn the bias on the human.
That's a good point. So if the algorithm is wrong and it's sending cars to it's sending cars to black neighborhoods just because that's where they make arrests more frequently, and then that feedback that's a positive feedback loop. And if there's racism in the environment, then they won't notice that, and they won't say, well, gee, we need a different algorithm. There's crimes being committed and there's police cars not being sent there because, if you send a police car to a black neighborhood, you can always find crimes or whatever. So there, like you said, there's inherent racism that has to be dealt with too. Otherwise, you won't notice that your model is biased, or you won't care about it.
So this kind of implementation actually also triggers what's called the Hawthorne effect in management.
Can you repeat that? Which effect is that called?
I think it's called the Hawthorne effect in management.
Hawthorne, like the name Hawthorne?
Yeah. So what happens is that if management pays special attention to a particular department or a particular worker, that department or worker starts performing better than the average.
And the same as in I think I've heard the same effect in elementary schools. If a teacher pays more attention to the smart students or to this or that student, maybe even not even smart students, maybe popular students or cute students or whatever, then they do better.
Yeah, and it works both ways, positive and negative. So basically, these are self-fulfilling prophecies that you can trigger off by accident.
I remember also the one of the image of a plane of the Second World War that they make the protect where that one.
Yeah,
it's almost the same thing.
Yeah, you're talking about the one where the British fighter planes were coming back, or maybe it was American, I can't remember which one. They were coming back and they would have bullet holes in them, and let's see, what was it that they decided, what were they going to do about it? This plane had bullet holes in its wings, and so
the issue was that they I mean, the statistical guy who was one of the heads of the statistical institute kind of pointed out that, so the inclination would be then to strengthen the areas where the holes are in the plane. But what he pointed out was the planes that came back with the holes, you need not strengthen there because they survived and came back. Where you needed to strengthen were the non-hole parts of the planes which came back, because if you're short there, then you went down and didn't return. So you need to kind of think about the negative of what is not there, which is not a human inclination that happens often.
Yeah, I forget who the statistician was that made that discovery or recommendation. That's a famous example about bias. But I remember there's sometimes people go to the extreme and try to say that there's bias when there may not be. And one of the examples that comes to me is, this was about maybe 10 years ago or more. They had this survey that people can take, a little test that people can take. I think it's still online, where they're trying to prove to everybody that they're biased, that white people are always biased against black people. So they show you pictures of black people and white people, and then at the same time you look at each picture, and then you have to pick the word good or bad or evil or whatever. And then they showed that in their study that people more likely pick bad words, negative words, when they're shown black faces than they do when they're shown white faces. But I did this, and I looked at it carefully, and I came to the conclusion that the effect there isn't real, because they show you, like, the white faces have neutral expressions on them, and the black faces have scowling or mean, mostly have negative expressions on their faces. And so I think they designed their study to get the effect that they wanted. I can't remember the name of the study, but it's a famous study, and I think it was done by Harvard, and it's still out on the web. They wanted people to take this. They wanted people to take this test on the web, and you could take the test and get an instant result to show you that you're biased against black people.
Actually, I think I came across some version of that study, and I think the point they wanted to make is an additional one, which is that at the same time they showed the picture, they showed a couple of opposites. And basically what it makes you do is to associate the white skin color and black skin color with one of these opposites.
Yeah,
immediately.
And they're always there, but the opposites are usually they're not neutral. Like, there's a good and a bad one. There's a good and a bad spectrum of responses,
Yeah, exactly.
And, yeah. And I just think that the data itself is biased, and that's why they got the result. That's my feeling about it.
Yeah, it was like quite similar to, did you see the picture that she showed of herself? One where it was like smiling and one where it was like scowling.
Yeah.
And she was going, oh yeah.
Yeah, like, black pictures from arrests, and when you arrest somebody, they're not likely to have a nice expression on their face when you take their picture.
Yeah, exactly. Like the picture of her smiling, you're much more likely to trust her and probably think that she's not going to commit a crime or whatever. Whereas the one where she had the really scowly face, you are likely to think she's going to do something bad. So
yeah,
if they have like sort of biased data like that, where they're sort of changing the people's expressions, it's not really going to give a true reflection of.
But I've never heard
people's opinions.
I've never heard anyone else have that response to that study. That was my response when I took it. When I took the test right away, and I noticed that the pictures are not neutral, that the white faces have neutral expressions and the black faces are more likely to have negative expressions. I'll post this on Slack to make sure that, you can, I'll find it, I'll dig it up, and I'll post it on Slack. Okay, so I guess we have next week, we have the last lecture, and it's a lecture on the future of NLP. And let's see, one of you has, I forget which one, one of you has said they'll cover that. So that'll be our last meeting on this class, and then we'll be finished.
Are there any plans to go further with this or look at more stuff at the end? I can't remember who published. Somebody put something up about sort of more the future of MLP and NLP and sort of more recent advances and things sort of that have come since BERT.
I don't have plans to continue it, but anyone can feel free to continue with it. I know there are some other groups, there's NLP, I forget, there's so many other Slack groups that sprung up at about the same time that we did. And they're actively doing things like reading papers, pursuing projects and so on in NLP. So that's one place that people can go. Let me quickly survey that. We have NLP embeddings, NLP papers, and NLP projects. These are 3 different Slack groups that sprung up about the same time we did. And Darren Kluchok is loosely connected. I think he's running all 3 of them. And some of you might be in them. I think Dinesh, you're in one or the other of them. Anyway, so that's one avenue that people could go. Any one of you that wants to go further is free to start up a new group, a paper reading group, or a group with, gathered around some particular area of NLP that you want to explore. That would be fine. Just use the, if you want to use the general channel to announce your plan and see how much support you can get for it. And if you get, I would say if you get, 20 people or so who are committed, who say they're committed to going to following this meetup, then you can go ahead and start one.
I know there is a CS224U group that went over another class, the other central class, but I think they're moving very slowly. I'm not part of that.
They're out of Europe, or out of England or Europe, I think. They meet on those time scales. I think, Dinesh, you're working with them.
Which class again?
The people who are doing the European version of hands-on ML, they've also started.
No. I'm talking about the different class. There is another class from Stanford.
Yeah, it's the same guy who was running the hands-on ML EU group, and he also is starting. He also started the NLP the natural language processing dash understanding course review.
I don't think that ever got started. So I'm not in it, but I don't think it got started. I'll check with it, Arshad, but I doubt it.
Yeah, Arshad. Yeah.
No, it hasn't. We started another one, which is NLP paper readings.
Yeah.
So.
Okay.
Yeah, but
so NLP papers, then NLP _papers, that's run by Arshad?
That's correct.
Yeah, I participate that group, and Dinesh also, right? But you skipped last meeting. Yeah, but, and there are not much people there, maybe because time is not very good. I don't know. It's on Thursday.
It's Thursday. Yeah, we need a lot more people. There are 2-3 people usually there. Yeah.
What time do you guys meet on Thursday?
It's Thursday GMT 4, so it's a PST 8 a.m. It's the same time this class start on a Sunday. So we Thursday.
Oh, okay. 8 a.m.
But maybe if there would be like a lot of interest in paper reading, we can, I don't know, discuss some more widely acceptable time for that.
So is there interest then in like an NLP paper reading group, or our own NLP paper reading group, or?
I'd be interested in like looking at some of the sort of more recent papers that have, progressed on from BERT, or like starting at BERT and moving on from that. So, I tried to turn up to, I think it was one of the Thursday afternoon ones. I didn't realize they were doing the things, like where you go along and everybody goes off and reads the paper. And so like it was all silent. And I turned up a couple of minutes late and didn't realize that everybody was reading the paper. I just thought everybody disappeared. So I didn't actually hang around, but it'd be interesting to sort of like have a look at sort of more recent papers maybe.
So what we have done,
people leave those groups, the silent reading groups, they should at least write a message to the chat saying, hey, we're silent reading and we'll join for discussion. We'll rejoin for discussion in 45 minutes or whatever.
Yeah, I thought my internet connection had gone down.
No, so Steve and we changed the structure of it. Now we are reading very loud. So even not one person would be reading. So it's like screen share. And then I'm like Arshad will read a 2-page and then I'll read a 2-page and then he will go 2-page, Artu will come in. So it's more interactive now. So not silent reading anymore.
Yeah, as I said, I didn't know what was going on. So it was strange.
What I was proposing, I was thinking maybe there would be, if there would be more people, there might be some people who would be interested in reading a paper, for example, once a week, and then presenting the core ideas, and we can then choose those papers which we want to study like in depth, because in such format as we have now, it takes a couple of weeks to read a paper, and there are like tons of paper coming out on NLP now, and that might be like very efficient to have multiple people's scanning through the papers and finding the most interesting stuff and then discussing it and going in depth in what we want.
That's a really good idea. So you would say something like, everybody go out and scan the literature and pick let's say 2 or 3 papers that you're interested in, that you might be interested in reading, and maybe don't read them yet, but just present the abstract. What is, in the meeting, when we meet all together, each person says, okay, here's the papers that I came across, and then present the abstract. And then we could choose, then at that meeting, we could then all choose which paper we want to collectively read and explore in detail. And then, so every week we could have, a few minutes of looking ahead to what the next paper will be, and then the main discussion, which is the paper that people selected last week. Is that something like that? Is that kind of in line with what you were suggesting, Arto?
Yeah, right. That's what I was thinking about. And also, like, different people have somewhat different interests and area of expertise, and it would be nice, like, to hear from those more experienced in some area about like current research.
Yeah. Also, I'm thinking that maybe it's not necessary to have everybody read the same paper, but that, as you said, there are so many papers coming out, and it's just, it's very overwhelming. But if we had a situation where, like, each meeting, we have maybe 3 people presenting, they've read the papers thoroughly, and they present the paper, present the outline of what the paper is doing to everyone, so that then everybody comes away from the meeting and they've learned 3 papers. They've learned the essence of 3 papers. And that's a way of multiplying our efforts.
Yeah, I totally agree.
Or maybe even more than, maybe we could even do more than 3 if we just had a quick summary of the key ideas in each paper without going into detail. So some of the meetings could be that, where everybody informs each other about what they've been reading. And then other meetings could be where we all go into depth on some paper or other, Yeah, so that's TBD. But I also wanted to mention that Wenchang had started a group on Kaggle_NLP, where they're attacking Kaggle problems that are specifically NLP in the NLP area. So that group also exists, and I think they're active. But yeah, I mean, I think I don't have time for Kaggle competitions. They kind of tend to be very intense. I would have time to read papers though.
So when Chan mentioned at our last meeting that him and another guy I met in New York, Isaac Dombrowski, they were interested in kind of starting a new group based on papers. But I don't know if it's going to be like within TWIML or it's going to be a meetup. Yeah, so that's another.
So if we want to start a new group on papers, then we could. Somebody would have to coordinate it, and it wouldn't be me. And they would want to write up, the idea